First up, we're going to explore an explicit method to solve the finite difference problem. So remember we had day phi by day t is equal to day squared phi by day x squared. That is the second derivative. So now we have a space and a time dimension. Okay, so for the space dimension, we can use a centered approach. That is, the second derivative of phi with respect to x can be approximated by phi at grid cell I plus 1 time n minus 2 times phi at grid cell I for time n plus phi of I minus 1 at time n divided by delta x squared. We then need to include our time dimension, so we can use a first forward difference for this. So that is day phi by day t can be approximated by phi at grid cell I for time n plus 1 minus phi at grid cell I for time n, all divided by delta t. Okay, so what do I mean by this? Well, let's say we have a grid. Now remember, we've only got one spatial dimension. So that means if this is our spatial dimension in the horizontal, we can write the grid cells I plus 1, and I minus 1. And that means in the vertical, we are actually working with a time dimension. So here we have time n plus 1, n plus 2. Okay, so if we substitute both of these equations back into our original one-dimensional diffusion equation, we get that phi of I at time n plus 1 is equal to lambda multiplied by phi I plus 1 time n minus 2 times phi I at time n plus phi of I minus 1 at time n plus phi I at n, where lambda is equal to our constant k multiplied by our time step and our spatial grid spacing. Now this is quite important because it means that the stability in convergence is going to depend on this term lambda, because it is controlled by the time and the space step. So if we had to just rewrite our weighting, we would have at grid cell I 1 minus 2 lambda. At time step n plus 1, we've got a weighting of minus 1. And at time step n and at grid cell I plus 1, we have a weighting of lambda. And at time step n and grid cell I minus 1, we also have a weighting lambda. So we can explicitly compute values for each node for a future time based on the present values at its current node and neighbors. And essentially, this is just the manifestation of Euler's method.